You know how AI models are getting incredibly powerful? We're talking language models that can generate text, code, even hold conversations.
Yeah, it's moving fast.
But here's the catch. Usually, running those really cutting-edge models requires just enormous computing power, right? Often tucked away in massive data centers, in the cloud. What happens when you want that same kind of intelligence, but not miles away? You want it right here.
On the device itself.
Exactly. On a drone doing inspection maybe, or a device understanding commands offline, or even like next-gen features on your phone.
Right.
You need speed and efficiency outside the cloud.
Exactly. And that challenge, it's really pushing the boundaries of AI architecture itself. I mean, for years, transformer models have dominated.
Oh, yeah.
Ever since that attention is all you need paper kind of shifted the landscape back in 2017. They're powerful, no question.
They absolutely are. But they do have a significant limitation, especially when you're dealing with lots of data in sequence, like long texts or time series data.
The scaling issue?
Yeah, their computational needs grow really fast, quadratically, right, with the length of the input sequence. So you double the data, the compute time doesn't just double, it quadruples, which makes long sequences really inefficient, resource hungry.
And that inefficiency, well, that's a major roadblock for these edge devices we're talking about.
Okay.
And that's where newer architectures like Mamba, which emerged just this year, 2024, they come in.
Right, Mamba.
Mamba is based on state space models, SSMs, and it offers a pretty radically different approach. It allows for sequence modeling in linear time.
Linear time, that's a huge step.
It is. It makes handling long sequences much, much more efficient, at least theoretically.
And then hot on its heels came Mamba 2, also this year, building on that foundation.
Yep, building on Mamba. Key researchers involved here, folks like Albert Gu and Tri Dao. Mamba 2 pushes the efficiency even further, often running significantly faster, like 8x faster than the original Mamba, while also improving accuracy in some cases.
Okay, so Mamba 2 is even better.
Now, the goal for a lot of applications isn't just, theoretical efficiency on paper, it's practical deployment on real-world hardware.
Those resource-constrained edge devices.
Exactly. Running AI locally offers big benefits. You get real-time response. You keep sensitive data private because it's processed right there.
On device, yeah. Less reliance on network connectivity, too.
Right, which opens up whole new application spaces.
So the sources you shared today, they center around this research paper called FastMamba. And it tackles this exact challenge, doesn't it?
It does. It looks at how you take this really promising Mamba 2 architecture and make it run, lightning fast and energy efficiently on a specific type of hardware. Hardware that's actually pretty well suited for custom edge acceleration, FPGAs.
Field programmable gate arrays.
Right. FPGAs are powerful because you can reconfigure them at the hardware level. You can basically wire them up to perfectly match the computation you need to do.
But they're tricky. Not like programming a GPU.
Definitely trickier to program efficiently. So the FastMamba paper is really a deep dive into the clever algorithmic and hardware innovations needed to get Mamba 2 running optimally on these platforms.
Okay, so our mission in this deep dive then is to unpack how these researchers actually approach this. What were the main roadblocks they hit trying to run Mamba 2 on FPGAs? What ingenious tricks did they come up with, both on the software side, the algorithm, and the hardware design side?
The toe design aspect.
Exactly. And, what kind of performance do they actually get? It sounds like a fascinating look at the cutting edge, really making powerful AI practical for the devices all around us.
So before they could build a solution, obviously they had to figure out where the problem was. They profiled Mamba 2, looked at where it spends most of its time.
The bottlenecks.
Right. And their analysis showed that particularly during what's called the prompt prefill stage, that's where you process the entire input sequence at once, the SSM block and the linear layers are the computational heavyweights. They consume most of the runtime.
Okay, SSM block and linear layers. Makes sense.
And what's really interesting, they found that as the input sequence gets longer, the proportion of time spent in that SSM block, it actually increases.
So it becomes even more of a bottleneck with more data.
Precisely. So any decent solution really has to focus on making those two parts, SSM and linear layers, incredibly efficient.
Okay, so what kind of math are we talking about inside those blocks?
Well, they're different. The linear layers, that's mostly about large matrix multiplications. Standard stuff in AI, heavy math, but it's structured.
Okay.
The SSM block, though, it's different. It involves a mix of more diverse, less structured element-wise operations. Things like additions, multiplications, and, crucially, some complex nonlinear functions.
Nonlinear functions, like what?
Specifically, the exponential function and something called soft plus.
Okay, so you've got heavy structured math in the linear layers, and then this mix of diverse, maybe irregular math with tricky nonlinear bits in the SSM block. And you need to run all of this efficiently on an FPGA, which, as you said, likes structured, predictable operations and isn't always great with, say, floating point math or complex functions.
Exactly. So how did FastMamba approach this?
Yeah, what was the strategy?
Their core philosophy is what they call algorithm and hardware co-design.
Ah, co-design. That sounds important.
It's key. Instead of just writing software for existing hardware or building hardware for existing software, they change both together.
Okay.
They actually modified the Mamba 2 algorithm to make it more hardware friendly while designing custom FPGA hardware specifically accelerated for that modified algorithm. It's a joint optimization.
Really tweaking both sides at once. Let's dig into the algorithmic side first. You mentioned challenges. One major one was in the linear layers, specifically with quantization. What was the issue there?
Right, quantization. So to make things fast and efficient on FPGAs, you often want to use lower precision math, like 8-bit fixed point numbers instead of, say, 32-bit or 16-bit floating point.
Fewer bits, less compute, less power.
Exactly. But they found that the activation values and the weights in Mamba 2's linear layers, they have these severe outlier distributions.
Outliers. Meaning?
Meaning a few values are just much, much larger than all the rest, like huge spikes in the data range.
Okay, and why does that make quantization hard?
Well, think about it. If you try to map a range of numbers that includes these massive outliers into a tiny 8-bit range, you have a problem.
Yeah.
You either have to dedicate a lot of your limited 8-bit representation just to capture those huge outliers, which means most of your common smaller values get very little precision.
Swashed together, basically.
Right. Or you just cut off the outliers, clip them, but that can really destroy the accuracy of the model. Neither option is very good.
Okay, that makes sense. So how did FastMamba solve this outlier problem to get accurate 8-bit quantization for those linear layers?
This is where one of their really clever algorithmic innovations comes in. They used a Hadamard transformation before quantizing.
Hadamard, like the matrix.
Exactly. Think of it as a mathematical pre-processing step. This transformation takes the values, including those severe outliers, and it sort of disperses the magnitude of those outliers across different annals.
Interesting. So it doesn't just chop them off, it spreads the impact.
Precisely. The end effect is that the overall distribution of values becomes much more concentrated. It has a narrower range. It's like taking a few really tall, sharp spikes and smoothing them out, making the whole landscape less extreme.
Ah, I see.
And that transformed data is then much, much easier to quantize accurately into 8 bits. You don't lose as much precision on the common values, and you don't have to aggressively clip the outliers.
So the Hadamard transform prepares the data for quantization.
Yes, and they showed this method, FastMamba LQ they called it, gave better accuracy after W8A8 quantization compared to standard techniques like normal Q or smooth Q. It's a really neat insight. Preparing the data can make quantization work where it otherwise wouldn't.
That is smart. Okay, so Hadamard helps with the tricky linear layers. What about other parts that needed quantization, like the convolution layer, parts of the SSM block?
For those components, they used a different technique called power of 2, or POT, quantization.
Power of 2.
Yeah, this is another hardware-friendly approach. It works by restricting the scaling factors used in the quantization process to only be powers of 2.
And why is that good for hardware?
Because multiply or dividing by a power of 2 in binary hardware, that's just a bit shift.
Oh, right. Super fast, super cheap.
Exactly. Way faster and less resource intensive than a general multiplication, so it makes the fixed point math much more efficient on the FPGA.
Okay, so clever quantization strategies, Hadamard for the outliers and linear layers, POT for other parts. But you mentioned the SSM block also has those tricky nonlinear functions, exponential and soft plus. Quantization alone isn't enough for those, is it?
No, not really. Those functions are computationally expensive in themselves, and they're also quite sensitive to using low precision math, implementing them directly and efficiently in fixed point hardware on an FPGA. That's tough.
So what do they do? This led to another core algorithmic innovation, right?
Yes, they turned to using approximations.
Approximations. Okay, for exponential and soft plus?
Yep. For the exponential function, they looked closely at how it's actually used within the Mamba 2 SSM's calculation, and they found that in that specific context, the input values are always negative.
Always negative, okay.
So they developed a specialized first-order linear approximation, basically a straight-line equation, but it was specifically tailored to mimic the exponential function just for that negative input domain.
Ah, so a simpler function that works well enough in the specific range they needed. Much easier to compute in hardware, I bet.
Much easier, especially with fixed point numbers.
Okay, so a tailored linear approximation for the exponential. What about soft plus? That's a different beast.
It is, and this is where they got even more clever, I think, really elegant. They leveraged a known mathematical property of the soft plus function.
Okay.
Soft plus has a kind of symmetry. Soft plus of x is mathematically related to soft plus of minus x. They found a way to exploit this property to transform the soft plus calculation itself.
Transform the calculation. How? And what was the genius part?
The genius part was how they transformed it. They realized that by using the symmetry property, they could actually compute soft plus by doing two things. First, performing an exponential calculation on a negative number.
Wait, the same kind of calculation they just designed the linear approximation for?
Exactly. And second, just adding the original input value back.
Hold on. So they designed a hardware-friendly approximation unit for the exponential function using negative inputs. And now, because of this mathematical transformation using the soft plus symmetry, they can use that very same approximation unit to help calculate soft plus.
Precisely. That's the elegance of it. This deep mathematical insight allowed them to reuse the hardware they already designed for the exponential approximation when computing soft plus.
Wow.
It means they didn't need two separate, complex approximation units. One specialized unit, cleverly designed, could handle both. That saves significant hardware resources.
That's incredible. Using the math itself to simplify the hardware design really highlights that academic principle you mentioned. Understanding the structure leads to better engineering.
Absolutely.
Okay, so summing up the algorithm side, they introduced the Hadamard transform to tackle outliers and linear layers, enabling good 8-bit quantization. They use power of 2 quantization elsewhere for hardware efficiency. And then these really clever linear approximations for exponential and soft plus, brilliantly leveraging the soft plus symmetry for hardware reuse.
Right, all designed to keep the accuracy loss within acceptable limits while making the math drastically more suitable for efficient fixed-point implementation on an FPGA.
Okay, now let's flip to the other side of that co-design coin. The hardware. How do they actually build the FPGA architecture to run these optimized algorithms efficiently?
So the overall architecture, as you'd expect, involves managing data flow between different parts, using buffers, etc. But the core is how they handled the computation.
And they designed custom processing units for that, didn't they? VPUs?
Yes, vector processing units. These are basically specialized hardware blocks optimized for the kind of math needed here. Combinations of multipliers and adders, the fundamental building blocks for neural net computations.
And you said there were different types?
They identified 5 key types, tailored for different operations within Mamba 2. Some are fairly standard vector operations, adding vectors, multiplying vectors, but they also designed specialized ones that perform reduction operations.
Reduction.
Yeah, where you take a vector of numbers and, say, sum them all up or accumulate them into a single scalar result. These different VPU types, they call them PAU, PMU, PMA, HAT, MET, are like specialized tools optimized for the specific calculation patterns in Mamba 2.
Okay, so they have these optimized VPU building blocks. How did they arrange them, especially for that critical complex SSM block?
For the SSM module, they designed a specific pipeline architecture using these various VPUs to handle all the fixed point calculations derived from the Mamba 2 equations. It's structured to follow the steps computing the intermediate values, the hidden state, the final output, processing the data through various VPU stages in parallel where possible.
And within that SSM hardware, is there a specific piece dedicated to those tricky nonlinear functions we just discussed? The exponential and soft plus approximations?
Yes, absolutely. This is a major hardware innovation, and it stems directly from that algorithmic insight about reusing the approximation. They built a dedicated SSM Nonlinear Approximation Unit.
Okay.
This unit is specifically designed for 16-bit fixed-point data, which they found was needed for accuracy in this part.
And this is the unit that cleverly handles both the exponential approximation and the soft plus calculation.
That's the one. Thanks to exploiting that soft plus symmetry algorithmically, the hardware unit leverages a common core component primarily designed for the exponential approximation on negative numbers. It uses clever routing, like multiplexers, to select the right data paths and reuse much of the logic for both functions.
So the algorithmic smarts directly translated into a smaller, more efficient piece of hardware.
Exactly, and the paper quantifies this benefit quite clearly. They compared the resources needed for their custom fixed-point approximation unit versus implementing those nonlinear functions using standard 16-bit floating-point units on the FPGA.
And the savings were significant.
Massive. Their dedicated unit saves 56% of DSP resources, those are the specialized multiplication blocks on FPGAs, and 49% of flip-flop resources, which are basic memory elements.
Wow, roughly halving the resources needed for that specific complex part.
Yeah, it's a huge saving on fundamental, often limited FPGA resources like DSPs, FFs, LUTs, RAM. It really demonstrates the concrete payoff of their co-design approach, finding that mathematical trick and building hardware around it.
Incredible savings. And presumably they used similar parallel VPU structures and pipelining for the linear and convolution modules as well.
Yes, the paper describes modules for those two, also built using parallel VPUs and designed for efficient throughput.
Okay, so putting it all together, the optimized algorithms enabling fixed-point math, the custom hardware with specialized VPUs, and that efficient nonlinear unit, what kind of real-world performance did FastMamba actually achieve on an FPGA?
Right, the results. They tested FastMamba on a specific Xilinx FPGA board, the VC709, and they compared its performance against a standard Intel Xeon server CPU and also a high-end NVIDIA GPU, an RTX 3090.
Good comparison points.
They looked at two main scenarios. First, speed up for the prompt prefill stage using a smaller Mamba 2 model, 130M parameters. Second, energy efficiency for the token decode stage using a larger model, 2.7D parameters, which is more relevant for inference. They also checked accuracy, of course.
Okay, let's hear about the prompt prefill speedup first. That's where you process the whole input at once, often memory intensive.
The results here were pretty dramatic. FastMamba running on the FPGA achieved a maximum speedup of 68.80 times over the CPU.
68 times.
Yeah. And maybe even more impressively, against the powerful RTX 3090 GPU, it still achieved a maximum speedup of 8.90 times. That peak was often at shorter sequence lengths, like 64.
Nearly 9x faster than a 3090 GPU on an FPGA. Wow.
The average speedup across the different sequence lengths they tested was still really strong, over 55 times faster than the CPU, and just over 6 times faster than the GPU, on average.
That's genuinely impressive performance. Nearly 70x the CPU speed, 9x the GPU speed for prompt prefill. And that speedup, it comes directly from that whole co-design package, right? The fixed point math enabled by their quantization tricks.
Right, the Hadamard, the PAT.
The parallel processing with their custom VPUs and the efficient pipeline hardware architecture.
Exactly. It all comes together.
Okay, what about the other scenario? Token decode, focusing on energy efficiency, which is critical for edge.
Right. This is more about generating output token by token, which is common in language models and often the bottleneck in real-time power-limited situations. Here, using a larger Mamba 2 model, they found FastMamba achieved 6 times higher energy efficiency than the RTX 3090 GPU.
6 times more energy efficient. That is huge for anything running on a battery or anything where heat is a concern.
Absolutely. It means you get 6 times more computation done for every watt of power you consume, compared to a high-end GPU doing the same task. That's a massive win for edge deployment.
And did they show where the resources were being used on the FPGA itself?
Yeah, they provided a breakdown, and as you'd expect from their initial bottleneck analysis, the linear module and the SSM module consumed the most resources, like DSPs and brands.
Confirms their focus was right.
Exactly. But it also highlighted the impact of their optimization within the SSM module, showing the significant DSP savings achieved by that specialized nonlinear approximation unit we discussed.
Okay, so bringing this all together, why does this deep dive into FastMamba matter for you listening?
Well, I think this research isn't just some abstract academic exercise, right? It's a really concrete example of how we bridge the gap between these incredibly powerful AI models being developed and actually deploying them out in a real world, outside of the cloud.
Making them usable.
Even them usable, successfully getting complex architectures like Mamba 2 to run this efficiently on-edge hardware like FPGAs, that's what unlocks the potential for truly pervasive AI. It means faster response times because the calculation happens locally. It means better privacy because your data doesn't have to leave your device. And it enables entirely new applications that just aren't feasible if you always need a connection back to a massive data center.
And it really hammers home the power of that algorithm and hardware co-designed philosophy, doesn't it?
It really does. This level of performance and efficiency, it wasn't achieved by just optimizing the software or just building faster hardware in isolation.
No.
It required the researchers Aotao Wang, Haikuo Shao, Shaobo Zhongfeng Wang were the authors on the paper to deeply understand the intricacies of the Mamba 2 algorithm and the capabilities and limitations of the FPGA target, and then to modify both symbiotically.
Tackling the problem on multiple fronts at once.
Yeah, It shows that sometimes the biggest leaps forward come from that holistic approach.
It also seems to show that FPGAs are still a really relevant and powerful platform for custom AI acceleration, right? Especially for newer models.
I think so. When you have a specific novel architecture like Mamba 2, which has unique computation patterns compared to, say, standard transformers, designing dedicated hardware like FastMamba's VPU-based system, it can yield performance and efficiency gains that more general-purpose processors, even powerful GPUs, just can't match for that specific task.
Right, tailor-made acceleration.
Exactly.
So, okay, to wrap things up then, FastMamba seems like a prime example of taking a really promising next-gen architecture, Mamba 2, and doing the hard engineering work to make it practical for edge devices.
Absolutely. They tackled those critical challenges head-on. Things like quantizing data distributions with those severe outliers, using clever tricks like the Hadamard transformation, and figuring out how to implement complex nonlinear functions efficiently by finding and exploiting mathematical properties like that soft plus symmetry, which directly enabled hardware reuse in their custom architecture.
An architecture featuring those specialized vector processing units and that highly efficient nonlinear approximation unit.
Right. And the results, well, they speak for themselves. Demonstrating really impressive speedups, yes, but maybe more importantly for the edge, those crucial energy efficiency improvements compared to standard CPUs and even high-end GPUs.
It's a fantastic illustration of the kind of deep algorithmic and hardware innovation that's happening, often at the academic and research level, to actually get these cutting-edge AI models out of the lab and into the diverse, resource-constrained environments of the real world.
Yeah, it's where the rubber meets the road, so to speak.
So here's something to think about. How will this relentless drive, this push for algorithm hardware co-design, for making powerful AI inference work efficiently beyond the cloud, right in our devices, how will that reshape the technological landscape in the coming years?
It's a big question.
What new experiences or capabilities become possible when sophisticated AI is truly ubiquitous, when it's low latency, energy efficient, and running right where the data is generated all around us?
It certainly changes what we can imagine AI doing in our daily lives.
Absolutely. It really opens things up.